let's start officially for the second Automation Research Spotlight by IEEE Robotic and Automation Society. My name is Birgit Vogelhäuser. I'm Chair of Automation and Information Systems at the Technical University of Munich. And I have the honor to introduce and host, together with my dear colleague Ciao Bo, this session today where Maria Pia, a very renowned colleague, will introduce a bit on her work on new approaches for last mile delivery management. Maybe I can shortly introduce Maria Pia. She is a full professor since a long time with the Department of Electrical Information Engineering of the Polytechnic of Bari. She was also involved in many case conferences. She has, of course, published many papers, books, and she is also at the moment very much in charge of the summer school, the first IEEE RUS summer school on automation, which will take place in 2 weeks in Bari. So, and today, as said, we are looking forward to her talk on new approaches for last mile delivery. We all know we are ordering a lot of things nowadays online, and we all know the last mile is the issue. How can our parcels get to us? And so we are really enthusiastic listening to your talk. Maria Pia, please share your screen, and whenever you are ready, please start. So we are very happy you're here, all the audience. And just to let you know, we are recording now. So if you don't want to be, let's say, recorded, you should not speak. And of course, later in the discussion, we will stop recording so that you can discuss with Professor Fanti freely without being recorded. Thank you so much, Maria Pia. Stage is yours.
Thank you. Do you hear me?
Yes.
And yes, do you see my screen?
Yeah.
Yes.
Perfectly well.
Thank you, Birgit, to give me this very interesting possibility to talk with a large number of people about my research for last mile delivery management. This is a talk, a contribution that is performed by the Laboratory of Control and Automation of the Polytechnic of Bari in Italy. And it is involved also in the Automation Logistics, Technical Committee on Automation Logistics, Technical Committee on Machine Learning for Automation. And this is the outline of my presentation. I will start with the motivation of this approach, of this research, some recall about the literature review, and our proposed approach that is based on digital twin, optimization, simulation, and also multi-agent reinforcement learning approaches. So I will present a case study and the conclusions. The motivation. Last mile delivery represents the final step of the delivery process, and the goods that are transported by big trucks have to reach the final customer. And the objective of the last mile delivery is to develop solutions that are able to enhance the efficiency and for decreasing the traffic in the urban area, increase the operational efficiency, and guarantee fast and prompt delivery. And this is also for responsive to the increase of demand while maintaining environmental sustainability. So it is a very important problem in our cities because the last mile deliveries are increasing in our city. And so it is very important to manage very well this kind of activity. In the literature review, we can consider different, very different approaches that are presented in the related literature, that are based on linear programming, meteoristics, AI-based approaches, energy efficiency algorithm. But innovative technologies can be used in order to improve the customer experience, in order to achieve sustainable growth in last mile delivery. Then what we can consider, we can in the gaps in our literature is considering real-time data integration in order to respond to real-world events, such as, for instance, the traffic changes, to using optimization and simulation strategies, to consider also the updating of urban infrastructure, because in some cases, the urban infrastructure are not suitable for improve the last mile delivery. And finally, what we would like to study and explore is the interaction with public and shared mobility resources, and in particular improve the decision-making operation that have to consider, as I said, the new updating of urban infrastructure, but also new techniques for the optimization of the last mile delivery. So the proposed approach. The proposed approach is based first on the application of digital twin, and in the digital twin, optimization, simulation, artificial intelligence tools. What we would like to propose? Proposing innovative urban freight transport and logistics with the aim of reducing traffic and improve the last mile delivery activities. In the standard delivery, what happens? A truck driver is responsible for transport, the fleets, and also to deliver product to customers. In the new approach, the truck is carried by a driver, but also can be truck that is autonomous. And then the deliveries are performed by robots that cover the last mile delivery actions. So this is the standard delivery flow. You can say that the truck starts from the warehouse, then go to the different zone of the city, where the truck driver delivers the parcel to customers. This is the current most frequent standard delivery in our cities. What we would like to propose? We propose a solution that some cities are starting to divide the city in different zones. In each of these zones, you can consider an hub where the trucks arrive and the parcels are unloaded, are loaded in robots, and are the robots that deliver the parcel to the customers. So this is the new approach, where the truck arrives just in one zone in one particular zone of the city, and starting from this zone, only the hubs, only the robots can deliver the parcel to the customers. So this is the approach. The different truck arrive in different zones of the cities. And from this hub, the robots start to deliver the goods, and then they come back to the hubs where they are unloaded again, loaded again with the new goods. And you can see some element that can be used in these activities. These are some robots that are used in particular during the pandemic period, when it was not possible to have the delivery performed by person, but by human, but in some city during the pandemic period, we used yet this kind of delivery. But now we would like to optimize this solution by considering to start with digital twin approaches. And indeed, we propose a digital twin that has to manage a set of hubs. A digital twin is a virtual representation of a physical object system or processes. In a digital twin has to simulate the real system by using real data, so that by the digital twin, the simulator at any time has a photograph of the system that is updated in real time by considering a set of sensors that are distributed in the city. So we consider the set of zone of the city, consider a set of zone where the hub is positioned. The digital twin is responsible for managing the last mile delivery in each hub. So the digital twin every day has to consider, has to have a simulation that is updated in real time of the real system. Every day a truck arrives, more truck arrive at the hub with a list of scheduled deliveries. So an optimization is executed offline at the beginning of the day to manage the robot in the hubs that are connected with the digital twin. So the digital twin, by using the optimization, optimize the number of robots that are distributed in the hubs, and also the routing that is assigned to each robot, so that each robot has to perform a set of deliveries, with a set of customers. In case of traffic congestion or road closures, the digital twin can perform the rerouting, can change the routing that the optimization provided at the beginning of the day. So we have these two elements in the digital twin. First, we have an application layer where the optimization is performed. In this application layer, the optimization has to decide the number of robots that must be distributed in the set of hubs that are managed by the digital twin, have to decide the set of customers that in each hub must be served, and this optimization has to decide the routing of each robot, because the robot can deliver more than one good at a time. It can deliver more elements, and so it is necessary to give also the routing, to optimize also the routing assigned to each robot. This is the application layer. You can see that in our approach, this digital twin is composed of 3 layers. In the second layer, we have the simulation. The simulation, as I said, it is connected in real time with the physical layer, that is the real system. And by using a connection with the real system, connection that is performed by cloud, for instance, and connection that is performed by sensors that are connected with the cloud. The cloud is connected with the simulator and with the digital twin. And in this way, the route that are provided by the optimization can be updated on the basis of the real-time data that comes from the physical layer. And some modification can be applied for rerouting, for change the route if this route is blocked, or a high level of traffic is detected. So, as I said, the digital twin is based first on the application layer. The application layer that in our approach is defined by a mixed integer linear programming problem, where the objective function is to minimize the total distance traveled by the robot, with some main constraints that are for each customer. Each customer should be served only once. The robot capacity, the maximum capacity of 3 parcels are performed by each robot. The robot load must not exceed the maximum capacity. The delivery time must respect also customer time windows, because also the customer have some constraint on the time. So the optimization results are the following: assigning robot to each cluster, the departure and the arrival times of robots to customers, the total travel time, the route, the sequences of deliveries for each robot, and distance traveled by each robot. And you can see, I don't give you the details, obviously, of the performed optimization module, but I would like just to point out some main specification that are necessary. Indeed, the nodes, we consider a graph that is a graph that model the city and the network of the city. And a node is a customer that must be served. And we have the set of hubs, the set of robots, and also some travel specification, for instance, the distance to travel from one node to another, the time to travel from one node to another, the service duration at each customer, the demand of the customer, in other words, the parcel unit that it is necessary to delivery, and also some specification about the robots, because the battery capacity of the robots is limited, and we have also a minimum allowed battery in each robot, and obviously the battery of each robot must be enough to perform the deliveries, but also to come back to the hub. So it is also the constraint about the battery that are important. The decision variable are variable that decide if a robot that travel from node, starting one node, ending in another node during the particular route must be performed. So we have also some variable for assigning the robot to the hub, variable for deciding the routing that the robot have to perform. And as we would like to point out, this variable that has related to the cargo load of robots and the battery that are assigned to each robot and the energy consumption of each node. Because, as I said, it is important to have the management also of the battery or to guarantee the delivery and to guarantee that the robot is able to come back to the hub. And then this is the optimization module. As I said, it is a mixed integer linear programming model where the objective function aims to minimize the total travel distance of the set of autonomous robots. And the second main objective is the determination of the number of robots that must be assigned to each hub. And we have a set of constraints about the robot routes, about the capacity of the robots, and as I said, constraint about the service, about time, about the battery, and about the deliveries for guarantee the delivery of all the parcel to all the customers. So this is a very complex model. And after we receive the output of the result of the optimization model, the optimization layer, then the simulation layer is implemented. And the simulation layer is part, as I said, of the digital twin and is connected with the real system. This, the simulation is performed in SUMO, the simulation of urban mobility. It is an open access simulator that is able to perform the simulation, but also to optimize the route by addressing uncertainty and traffic congestions. And as I said, the physical layer is the layer that transmit, send the some real-time observation that comes from the real system that are, for instance, the traffic flow, the vehicle's position, unexpected events, congestion, road closures. And this, it is on the basis of this data, the collection and the knowledge of this data, that the simulation is updated. And on the basis of the obtained simulation, we can modify vehicle travel, delays, fuel consumption, delivery efficiency. The simulation, as I said, is performed by Urban Traffic Simulator, that is SUMO. And this simulator is based on the Google Street Map, that is a tool to obtain the city network. And this simulator reproduce, mime the network, the behavior of the network of the system, considering, as I said, the real traffic. Moreover, there is a tool in SUMO that is TRACI, Traffic Control Inference interface, that enable the bidirectional communication between the simulator and the control applications. And event and scenario evaluation can be considered in order to set up the route that are previously given by the optimization, in order to modify eventually this routing to consider the real-time events and the real-time operations. And you can see the case study that we develop based on two hubs that are considered in the city of Bari in Italy. And you can see the two hubs and the set of deliveries, the set of customers that are associated to each hubs. These are on the basis of the optimization. We have to divide the number of robots in each hub for optimize the delivery. And moreover, the optimization provide also the routing that each robots have to perform. This is the results of the optimization. These are the set of robots that belong, a set of 8 robots belong to the first hub, and a set of other 8 robots have to consider in the second hub. And these are the routes that are associated to each robot. For instance, the first robot in the first hub has to perform 2 routes, one with 3 customers, one with 1 customer. And so these are the routes, but these are just the number associated to the customer, but these customers are selected in order to optimize the route on the basis of the distances between each node and the other nodes. And for instance, this we have also this K16 of Hub 2 that is able to perform 3 routes, one for only one customer and the other 2 for 2 customers. This is optimized by the optimization, not in real time, before the starting of the job. And now this is also the optimization results, and to each robot we can show the travel time, the travel distance, and so on. So that this is what the optimization provide for the robots. Now, after this optimization, the simulations can start. Obviously, we have also simulate the performance of the digital twin, because we don't have installed now the digital twin. So we have considered as scenario 1 the simulation baseline, that is the simulation obtained just considering only the optimization. In scenario 2, we consider the simulation with real traffic. In scenario 3, we mime the situation in which the digital twin suggests, on the basis of traffic, the rerouting. And finally, in a final scenario, we simulated the standard situation of today, where the current situation where the deliveries are performed by the trucks that have to stop in different zones of the city. And in this case, we consider the emission control parameters to evaluate the environmental impact that are related to the emission and the fuel consumption for these deliveries. And these are the results, and you can see that with the Sumo simulation with traffic, the time for the deliveries increases, but using Tracy that is able to perform, to suggest the derouting, we found that 25 minutes are obtained with respect 25 minutes of decreases of for the travel time is obtained with respect to the optimization, a 15 minutes without the rerouting. So also, as I said, the comparison with the standard last mile delivery that is performed by 2 trucks that operate the deliveries in the 2 hubs, the emissions are very high. So the robot, the application of the robot improve the environmental sustainability very high, in a very high way, by reducing the CO2 emission, CO emissions, NOx emissions. And also the average waiting time decreases. So we consider the solution is a very good solution, even if, as I said, it is necessary to upgrade not only by using upgrade not only the optimization strategies, but it is necessary to upgrade the cities with hub, with sensor, with a digital twin. So it is a choice that the cities have to perform to obtain a better result in the last mile delivery. Now, a new strategy to substitute the optimization. Indeed, when I present the application layer, as I said, I perform a standard optimization. It is a mixed integer linear programming optimization. It is a standard solution that can be applied in the logistics area. Now, a new possibility is to substitute the optimization with a multi-agent reinforcement learning approach. So delivery robots learn optimal policy through the interaction with the environment and with the other agents. So this is a very new strategy that uses the simulation, uses the digital twin to optimize the route that are not performed by only the standard optimization, but are performed by multi-agent reinforcement learning. And the multi-agent reinforcement learning approach is important in this context because multi-agent reinforcement learning extend the concept of the reinforcement learning. Multi-agent because each agent in this case is a robot, and it is this robot that, by observing the state of the system, has to learn and on the basis of the observation, has to learn the optimal action that must be performed. And in this case, the robots are not only agents, but are agents that have to collaborate each other. So this is the very important aspect, because if the advantages with respect to the standard reinforcement learning is to have more stationary solution, because multiple agents that learn simultaneously and change their policy, sometimes it is difficult for an agent to decide if a reward change for the own action or for the behavior of other agents. This is why it is important to have more agents that collaborate. Then exponential growth of action space. In this case, if more agents collaborate each other, then the action space is not too large, not doesn't grow exponentially. Then the partial observability. Indeed, agents that has, in some cases, partial local observations, it is important that collaborate each other, communicate each other to share information among them. So it is, this is why it is important to have multi-agent reinforcement learning approach. By using this approach, we guarantee a coordination of among the robots that share information and can optimize collectively their routes. Then we can use scalability and flexibility, because in this way, the number of delivery vehicles can increase, And the approach can be maintained efficiently, also with if the number of vehicles increases. The dynamic adaptability, indeed, this multi-agent reinforcement learning enables vehicles to adapt to changing conditions in real time, and also to adapt in real time with rerouting to answer to an expected obstacle or accident, as I said before. But in this case, they are the agents that autonomously learn this new, the strategy that they have to follow. As I said, agents in this case are robots. The environment is modeled by the city network, also in this case is modeled by Sumo. And this is the way to train the agent. We have a set of actions. The set of actions are the set of possible roads connected with the current position in the network. And we consider the state of the agents, that of the state of the robots, that in this case is composed of 4 elements. The current road, the position of the robot, in other words, the current road in the Sumo network. The battery level, as I said before, it is important to know the remaining battery percentages. And the number of delivery that they have completed, the next delivery target, the age corresponding to the next delivery location. This is the state of the agent. The reward. The reward must be positive for successfully reaching the delivery destinations. For instance, we have to give a positive reward if the agent select the best route, if the agents have a high level of energy consumption, the agents are penalized. So the contrary of a reward. The penalty are given if the agents have a high level of consumption, or they fail to maintain sufficient battery to complete their work or their job. And penalty for invalid actions. The agents are incentivized to return to the hubs. And collaboration. The agents have to collaborate, in other words, the robots have to collaborate each other. And agents receive additional reward for completing deliveries in collaboration with other agents. So robot in collaboration with other robots. And finally, a total reward is a weighted sum of the reward that we given to the reward that we given to the robots. And you can see the training results. We consider in this case 3 agents, so we consider 3 robots. The result of the energy consumption, the result for the time for reaching the final destination, and also the average time of each training session for each delivery performed by the agents. This is a good result, because in this result we can see that at the beginning of the training, the agents perform the right, don't perform the right selection of the route. On the contrary, after the training and after the different scenarios, the agent improve the policy, and progressively they perform the right deliveries. Now, the conclusion. We provide new strategies for the last mile delivery. It is a very crucial problem for our cities, where this kind of deliveries door to door increases. So it is very important to solve this problem, to propose the new strategy to solve this problem. And our strategy is based on digital twin that is related to the real-time situation is the city, but also with optimization and simulation. Optimization, I show in my presentation, the standard optimization that use mixed integer linear programming problems, but also new strategies that are based on artificial intelligence and deep reinforcement learning. And this is, in my opinion, the future. The future is to improve this algorithm, considering the larger number of robots, and consider also implementation, re-implementation in the cities, so that the robots can be trained by receiving real data from the real system, the real cities. And as I said after each of my presentations, I have to thank the people of my lab that allow us to reach these results. And they are PhD students, postdoc, professors. And thank you to you for your attention, for giving me this very good possibility. Thank you to Birgit. Thank you for the Robotic Automation Society to give me this possibility.
Well, thank you very much, Maria Pia. I think we should give a nice thank you to you. So thanks a lot. It was really amazing. So there is room for questions. So does anyone from the audience like to ask a question? So I think we stop recording then, and so that we can really openly